And it turns out the beauty of the math is that if you compare these two configurations, before the nudging and after the nudging, you've got all the information you need to find the gradient.
Training the network involves simply repeating this process of equilibrium propagation over and over, using lots of labeled data. You can also find the constraint that neurons can learn only by reacting to their local environment in new theories of how the brain perceives. Baron Millage is a doctoral student at the University of Edinburgh and a visiting fellow at the University of Sussex. He and his colleagues have been reconciling this new view of perception, called predictive coding, with the requirements of backpropagation. He says if you set up predictive coding in a certain way, you'll get a biologically plausible learning rule. Predictive coding assumes that the brain is constantly making predictions about the causes of sensory inputs. The process involves hierarchical layers of neural processing. To produce a certain output, each layer has to predict the neural activity of the layer below. If the highest layer expects to see a face, it predicts the activity of the layer below that can justify this perception. The layer below makes similar predictions about what to expect from the one beneath it, and so on. The lowest layer makes predictions about actual sensory input, say the photons falling on the retina. In this way, predictions flow from the higher layers down to the lower layers. But errors can occur at each level of the hierarchy, from the prediction that a layer makes about the input it expects to the actual input. The bottommost layer adjusts its synaptic weights to minimize its error based on the sensory information it receives. This adjustment results in an error between the newly updated lowest layer and the one above, so the higher layer has to readjust its synaptic weights to minimize its prediction error. These error signals ripple upward. The network goes back and forth until each layer has minimized its prediction error. Millage has shown that with the proper setup, predictive coding networks can converge on much the same learning gradients as backprop. This brings it close to backprop gradients. But for every backward pass that a traditional backprop algorithm makes in a deep neural network, a predictive coding network has to iterate multiple times. Whether this is biologically plausible depends on exactly how long this might take in a real brain. Crucially, the network has to converge on a solution before the inputs from the world outside change. Still, if some inaccuracy is acceptable, Millage says predictive coding can arrive at generally useful answers quickly. Some scientists have taken on the nitty-gritty task of building backprop-like models based on the known properties of individual neurons. Standard neurons have dendrites that collect information from the axons of other neurons. The dendrites transmit signals to the neuron cell body, where the signals are integrated. That may or may not result in a spike or action potential, going out on the neuron's axon to the dendrites of postsynaptic neurons. But not all neurons have exactly this structure. In particular, pyramidal neurons, the most abundant type of neuron in the cortex, are distinctly different. Pyramidal neurons have a tree-like structure with two distinct sets of dendrites. The trunk reaches up and branches into what are called apical dendrites. The root reaches down and branches into basal dendrites. Models developed independently by Cording in 2001 and more recently by Blake Richards of McGill University and Mila and his colleagues have shown that pyramidal neurons could form the basic units of a deep learning network by doing both forward and backward computations simultaneously. The key is in the separation of the signals entering the neuron for forward-going inference and for backward-flowing errors. Those could be handled in the model by the basal and apical dendrites, respectively. Information for both signals can be encoded in the spikes of electrical activity that the neuron sends down its axon as an output. Richards says his team's latest work has gotten to the point where they can show that using fairly realistic simulations of neurons, you can train networks of pyramidal neurons to do various tasks. And then using slightly more abstract versions of the models, they can get networks of pyramidal neurons to learn the kinds of difficult tasks that people do in machine learning. An implicit requirement for a deep net that uses backprop is the presence of a teacher, something that can calculate the error made by a network of neurons.
There is no teacher in the brain that tells to every output neuron, say, neuron in the motor cortex, you should be switched on and you should be switched off.
That's Pieter Roelfsema of the Netherlands Institute for Neuroscience in Amsterdam. Roelfsema thinks the brain's solution to the problem is in the process of attention. In the late 1990s, he and his colleagues showed that when monkeys fix their gaze on an object, neurons that represent that object in the cortex become more active. The monkey's act of focusing its attention produces a highly selective feedback signal for the responsible neurons.
It's not an error signal, it's just saying to all those neurons, you are going to be held responsible.
Meaning responsible for an action. Roelfsema's insight was that this feedback signal could enable backprop-like learning when combined with processes revealed in certain other neuroscientific findings. For example, Wolfram Schultz of the University of Cambridge and others have shown that when animals perform an action that yields better results than expected, the brain's dopamine system is activated. Or in the words of Roelfsema,
it floods the whole brain with kind of neuromodulators.
The dopamine levels act like a global reinforcement signal. In theory, the attentional feedback signal could prime only those neurons responsible for an action to respond to the global reinforcement signal by updating their synaptic weights. Roelfsema and his colleagues have used this idea to build a deep neural network and study its mathematical properties.
It turns out you get error backpropagation. You get basically the same equation, but now it became biologically plausible.
The team presented its work at the Neural Information Processing Systems online conference in December.
We can train deep networks. It's only a factor of 2 to 3 slower than backpropagation.
Roelfsema says that beats all of the other algorithms that have been proposed to be biologically plausible. Still, concrete empirical evidence that living brains use these plausible mechanisms remains elusive. Benjo says he thinks we're still missing something.
In my experience, it could be a little thing, maybe a twist to one of the existing methods that's going to really make the difference.
Meanwhile, Yammans and his colleagues at Stanford have suggestions for how to determine which, if any,